I find it's useful to think of explainability as a continuum. On one end, you have purely deterministic, single-threaded procedural code. Do this, then that, then this, then that. When you run the program, you'll see it do those things, and it'll be really easy for you to determine why. On the far end of the continuum, you have deep neural networks and other high-dimensional adaptive systems. We give it an input, it does something, and then it returns an output. These kinds of systems are opaque, unstable, and highly sensitive to input variations. This makes them powerful, but also unpredictable, difficult to debug, and nearly impossible to explain. But researchers are trying to change that. There was a global push, including regulatory mandates, toward the development of models that we can understand. When a model returns a given output, we want to be able to say why it did that, not just describe the mechanisms it used to arrive at the answer, but describe the actual reasoning process. And this, generally, is the subfield of AI explainability. Today's paper provides a new approach for certain types of explainability, a new dual method that combines both feature-based explanations and example-based explanations as complementary perspectives to provide a more holistic understanding of the model's decision-making process. Modern ML models, particularly deep neural networks, apply sequences of non-linear transformations to raw input data, progressively encoding abstract representations that become increasingly difficult to interpret. Since these adjustments occur in high-dimensional space and often involve thousands or millions of parameters, the direct relationship between an input and its corresponding output becomes non-trivial to extract.